Hi, and welcome to Lesson 4A here in our Kinetics, Thermodynamics, and Equilibrium unit. In Lesson 4A, we're going to be dealing with equilibrium expressions. And of course, the letter after the number means that we're talking about an honors-only lesson. We should also pause here and note that we're really only doing a brief introduction to the concept of equilibrium expressions in this lesson. We'll be dealing a lot more with it in class through practice examples and discussions of what it actually means. That noted, let's go in. Mathematically, what we're most interested in when we deal with equilibrium expressions is what's called the mass action expression, KEQ, also known as the equilibrium constant. This is just a mathematical expression that relates the amounts of products and reactants at equilibrium. We can express this a lot of different ways, but for our purpose, it will always be expressed as follows. For a particular reaction at equilibrium, KEQ is mathematically equal to the product of the concentrations of the products in the reaction to the power of their coefficients multiplied by each other, divided by the products of the concentrations of the reactants to the powers of their coefficients multiplied by each other. Essentially, it's the concentrations of the products divided by the concentrations of the reactants, with that little wrinkle having to do with raising these things to the power of their coefficients. One quick note here is that putting square brackets around a substance is a chemical shorthand that just means concentration of that substance. We'll see that again in our next unit. This equation is on your honors reference tables, and so if you ever get confused about this, you can always go there to get it. KEQ tells us how much of a product is formed when a system reaches equilibrium. That's really what it's informative for. There are 5 major points that are really useful. The value of KEQ could be 0, in which case there is no reaction. All of the substance is remaining in our product form. The reaction really never started, so the rate of our forward and reverse processes is 0. KEQ could be less than 1, in which case there's more product than reactants because our denominator in our KEQ expression is larger. It could be 1 exactly, in which case the concentrations of our products are equal to the concentrations of our reactants. It could be greater than 1, in which case the concentration of our products is greater than the concentration of our reactants. Or it could be functionally infinite or incredibly large, in which case the reaction went to completion. These are the 5 major values that are very important. The bottom line here is that the bigger the KEQ value, the closer our reaction went to completion and converted entirely into products at equilibrium. Does this make sense? I wouldn't blame you if it doesn't. Take a moment and write down any questions that you have before we move on. When we talk about solubility of substances, we're interested in what's called KSP, which is the solubility product constant. This is a mathematical expression that relates the amount of dissolved ions at a solution equilibrium. For a reaction where a solid substance AB is dissolving into ions A plus and B minus and reaches a solution equilibrium, KSP is equal to the product of the concentration of the dissolved ions to the power of their coefficients multiplied by each other. We're not dividing by the undissolved salt in this. The reason for that is a little bit complicated, but has to do with the fact that it would be what's known as a heterogeneous equilibrium, which enables us to discard the undissolved salt from our equilibrium calculation. This is also on your honors reference table and will be available to you whenever you need to use it. You also have an honors reference table that deals with solubility product constants. This is honors reference table A, which is a table of solubility product constants for almost insoluble salts at 1 atmosphere and 298 degrees Kelvin. You can see that even though all of these things are listed on regular Regents reference table F as insoluble, they are slightly soluble. But their solubility products are incredibly small, which means that very, very little of them dissolve before the substance reaches equilibrium and starts precipitating out. The bottom line here is that the smaller the KSP value, the less dissolved salt there will be at equilibrium. Does this make sense? Again, this is tricky stuff, so if you have any questions, you definitely want to write them down before we wrap up. Thanks so much for watching our discussion of equilibrium constants. Make sure you can do the following things here at the end. Make sure that you can explain what equilibrium constants represent and why they're useful when we investigate equilibrium systems. Also make sure that you can represent equilibrium constants algebraically when provided with chemical and solution equilibrium equations. If you can do all these things, you're doing great. If not, that's really okay too. You can always leave the comments below the video and you can always get in touch with me. And like I said, these are things that we're going to be talking about a lot more in class because it works a lot better when we do these things together as a group than when we do them over video. Thanks again for watching. I really appreciate it. Have a great day.